So this is part 2 of class on May 1st, 2020. We've talked about factors that affect reaction rate, and I've referred you to the videos where other teachers are doing demonstrations illustrating these concepts. We're going to have to handwrite the second section of this presentation because of superscripts and subscripts and the problems that they bring with them when you're typing. All right, so the first thing I want to consider is a chemical reaction which is generic. So if I have A plus B turns into C. And we'll assume that the balanced equation includes some coefficient X in front of the A, some coefficient Y in front of the B, and some coefficient Z in front of the C. For reasons that I'm not going to be able to get into this year, given our circumstance, I'm just going to let you know that the rate of this chemical reaction is proportional to the concentration of A, and that's going to be multiplied by the concentration of B. Both of them will be raised to their coefficients. So the coefficient for A was X, the coefficient for B was Y. You'll recognize that we have a proportional sign, and a proportional sign begs for a proportionality constant, so I'm going to rewrite the equation with an equal sign and a proportionality constant called K times A raised to its coefficient times B raised to its coefficient. All right, so the coefficients become the exponents. The coefficient X became the exponent. The coefficient Y became the exponent. These brackets, the brackets that I've been writing, when you see those, that means concentration in moles per liter, which is also known as molarity. We've talked about that before, but moles per liter means molarity. All right, so the brackets, moles per liter, is molarity, M-O-L-A-R-I-T-Y. So looking at the factors that affect rates we've talked about, the nature of the reactants, temperature, concentration, surface area, and catalyst. It turns out that the most important of those factors is concentration. When we do problems with these concepts, you'll see temperature referenced also, and that's to remind you that everything we do is only valid at a particular temperature because temperature changes the collisions. Ultimately, it's all about concentration when we do calculations with these concepts. So that's why we see the brackets meaning moles per liter, which is concentration. All right, moving back to my generic example, this is the forward reaction. And forward, would you say forward would mean left to right or right to left? So when we talk about a forward reaction in chemistry, we're talking about going from left to right. Now I could write a rate law for the reaction if I just changed this to make it C, if I went the other way with it, like that, so C turns into A and B, the rate law for that reaction would be called R reversed, and that would equal K reverse multiplied by C raised to its coefficient, which would be Z. So those are equations for rate laws. This isn't oversimplified because we are making an assumption that when A combines with B to make C, that it is a single-step process. And if that's true, then these exponents will be correct, and this will be the correct rate law. However, most chemical reactions are not single-step reactions. So if we were doing a thorough job on this, I would be showing you how to calculate what these exponents are. But for this year, we're going to assume that the reactions are single-step reactions and that the exponents were the coefficients in the original equation. In a chemical reaction, if there are multiple steps, which most of them are, the rate is actually determined by whatever the slowest step is. So just to give an example of that, if you were going to do a mailing and we wanted to mail a letter to 100 people, we might have one person folding the letter, another person putting it in the envelope, another person writing the address. So I'll write these down. So you got a folding process, you've got a stuffing process, you need to write an address, and you need to put on a stamp. So which one of these steps would be the slowest? It'd be whoever has to write the address. So you're folding, stuffing, addressing, and stamping. Addressing is the slowest. So you wouldn't be able to get the process finished any faster than whoever is putting the address on could write the addresses. And that would be limiting your speed. We call that in chemistry, this addressing step would be called the rate determining step. Well, that's what if you have a series of steps, for the rate determining step, the coefficients will become the exponents. So I'm trying to show you how I oversimplify a little bit because I'm not considering the multiple step process. But with that being said, bottom line, these coefficients will become the exponents. All right, so now if I was at equilibrium, what does equilibrium mean? So we're going to transition into the concept of equilibrium that I wanted you to watch over here. So I'm going to pull this movie up, show you a couple things about it. So we have a guy here with a couple of trays, and there's water in this one, there's nothing in this one. We're going to transfer the water back and forth between the trays. So he's got beakers. Notice the beakers that are the same size. So what he's going to do is dip and pour in here, and then dip and pour back. So we'll watch what happens as time goes by. You can see that the process of dipping and pouring eventually led to both trays having something in them. And if he keeps doing this, he could do it forever, and the water levels would stay the same because you're putting back and forth equal amounts with each transfer. So the water levels won't change. Now, in another scenario, he dumped that one. We're going to use different beakers. See how we've got a bigger beaker and a smaller beaker? We're going to watch just for a second. So he's going to make this happen. So he's transferring.
Big scooper will always outdo the little guy.
You can watch this. I'm going to mute his sound, but you can see, this video is linked on the website. Eventually we're going to hit an equal rate of exchange, but when we do, the levels of water are not going to be the same. So the equilibrium, when we talk about equilibrium in chemistry, we're talking about equal rates of exchange. You'll notice that's about 140. This is about 140. They're different size beakers, but we're trading back and forth 140 each time. When we do, we've reached the water levels are going to be constant, and the rate of exchange is constant. So equilibrium means the rate of exchange is constant, not that the concentrations are constant. So you see, this has got more stuff in the container, but the rate of exchange is the same. So equilibrium means equal rates. Equal rates. Now up here, we just wrote a couple of rate equations. So if this reaction at the top is at equilibrium, then this rate will equal this rate. Excuse me, let me rephrase that. This rate will equal this rate. So the forward rate will equal the reverse rate, which I could write R forward, going left to right, will equal R reverse, going right to left. Just like up here, the rate of exchange of reactants to products is the same as the rate of products becoming reactants. So in equilibrium, reactants go both ways. This year, we've assumed that whatever we started with would eventually end up over here, and there wouldn't be anything left over here. Now we're looking at equations that go both ways to end the year. All right, so the rate of the forward reaction would equal K forward. I'm putting the equation in from up here. K forward multiplied by A to its coefficient and B to its coefficient, and that would equal K reverse multiplied by C to its coefficient. Now I'm going to divide both sides by K reverse and divide both sides by A to the X, B to the Y. So when I do that, this is an algebra rearrangement, I have K forward divided by K reverse is equal to C to the Z power, its coefficient, divided by A to the X power and B to the Y power. Now this is a ratio of constants. So this constant divided by this constant, that's equal to what we call in chemistry the equilibrium constant, KEQ. So KEQ is a ratio of products to reactants. Did you notice that the C is the product in this chemical equation? These are the things that react. So if we divide the products by the reactants, we will get the equilibrium constant. There's an equal sign. Now you have to raise the products to their coefficients. I just put CoF up here to remind you, and CoF. So that is the beginning of how to do equilibrium calculations. I'd also like to remind you before we end this segment of class that if KEQ, since KEQ is a ratio of products over reactants, if KEQ is big, so if you have a big KEQ, then that means that the products are favored. So I'll put more products. If you have a small KEQ, that means there are more reactants. And the reason for that is since it's a ratio of products over reactants, if it's big, that means the numerator is big. If it's small constant, that means the denominator is big, and that's the reactants. So when you have a small KEQ, that means there's more reactant than there is product. If you have a big KEQ, that means there's more product than there is reactant. All right, I'm going to stop this section of the video there, and then we'll take a look at some problems in the third section.